Alrighty, I think we got everyone inside from the waiting room. And without further ado, let's get started. So hello and welcome everyone to PTC's Waterloo's IoT panel. My name is Jackson and I am the co-president of Project Tech Conference's Waterloo region. I hope everybody is having a great day and staying safe. And just before we get started, for everyone that joined, just make sure that your camera is off and your audio is muted. And that way we can have a smooth experience. And today, we're super excited to have two panelists here today to share with you their experiences in the field of IoT and answer any questions you may have related to the field. And before we begin, I would like to quickly go over today's itinerary. So we'll be having each panelist give a short intro about their expertise, where we can gain kind of a more in-depth understanding of IoT. At around 7:35, we'll begin with the Q&A session where the panelists will answer your questions. So this does mean that you are involved as well. Please send any questions you may have to the Zoom call, and you can be sure to send it to either the public channel in the Zoom call or as a direct message to Lucigue or Keith. You can search them up inside the channel or in the chat and be sure to send the questions to them. And you can also search for them. Oh, sorry. And they will relay the questions to me and I will ask the panelists and hopefully have them answer your question. Our Q&A session will run for roughly 20 minutes and at around 7:55, we'll have the closing remarks. With that out of our way, let's get started. So we're excited to introduce you our first panelist, Professor Mahesh Tripunitara in the Department of Electrical and Computer Engineering at the University of Waterloo. So Professor Tripunitara has received his PhD in computer science at Purdue University, and he has worked in software development in Silicon Valley and took a role of principal research staff in the Security and Privacy Technology Lab at Motorola's corporate R&D labs in Schaumburg. And now currently, he researches information on information security, more specifically in areas such as authorization, access control, cryptographic key transport, secure payments, usable security, and security and reliability of computer hardware. The stage is yours.
Okay, can you hear me well?
Yep.
So I'll share my screen so that I can bring up my presentation. You can see that, I take it?
Yep, crystal clear.
Okay, great. Yeah, thanks Jackson for the introduction. As the slide says, any opinions that I state here are mine, not the university's. Right, so today I'll speak to an aspect of IoT in which I have done some work. So let's start with the working definition of IoT. Here's a working definition. It's billions of connected heterogeneous devices. And this definition, as you can see, calls out three attributes that I think are characteristic of IoT. One is the scale, billions. The other is the fact that they are connected. And so, of course, you have lots of attributes that are typically associated with connectivity. And the third is the heterogeneity. So this picture clearly kind of calls that out. For example, your toaster oven and your car could potentially be on the same IoT sort of network. Now, I'm going to start by focusing on the heterogeneous aspect and turn it around and say that even though at some level of Zoom, IoT is heterogeneous devices, comprises heterogeneous devices, really there are some fundamental building blocks to IoT. And I'll speak to one of them today, and that is digital integrated circuits, or ICs. What is a digital IC? It's a physical realization of some logic. And it is a fundamental building block of IoT. So even though in the previous slide, I suggested that the devices are heterogeneous, well, they are in some ways, but in other ways, for example, the fact that they all have one or more ICs embedded in them, they're homogeneous. So as my focus will, after this slide, turn to security, I will kind of talk about security of digital ICs, which is, of course, given that it's a fundamental component of IoT, is part of the security of IoT itself. So to the left of this picture, there's a simple digital IC, which is an adder circuit. Its function is to add the two bits A and B. And there's a third bit, which is a carry-in bit. So this is a bit like, you know, if you think of adding base 10 numbers, well, if you're going to add 10-digit numbers with one another, you can think of breaking it into adding digit by digit, but then having a carry digit from a previous addition. This is exactly how it is, except that this is base 2, binary. So the result of the circuit, the outputs are S and C out, which is the sum, which is 1 bit, and a carry out bit. And as you can see, a digital IC comprises gates and wires. In this simple example of the full adder circuit, gates 1 and 3 are XOR gates, gates 2 and 4 are AND gates, and gate 5 is an OR gate. So you have different kinds of logic gates. Now the colorful picture to the right, what it expresses is sort of the opposite of the black and white picture to the left. What it expresses is the complexity of modern ICs. So modern ICs realize complex logic. Okay, so let's talk about security, which is a particular focus of mine, as Jackson said in his introduction. And from the standpoint of securing ICs, what is a kind of insecurity that can exist? That is what this slide tries to communicate. And one of the sort of basic insecurities is theft of intellectual property. So the circuit, which is the digital IC, the integrated circuit, the logic that is embedded in it, is really, many people would perceive that as their intellectual property. So it's like you come up with a smart idea for a program, for example, a software program like a game like Angry Birds. Well, that's your IP, and you don't want somebody else stealing it and replicating it. And it's the same thing with digital ICs. So in this picture at the top, with the background of green, I present sort of an overview of the design and synthesis process, the way ICs are manufactured. And at the bottom, I have an attack, which is a reverse engineering attack, which is kind of like the opposite of the process from the top. So just to kind of focus on the top green bar, we have what is called, IC people call a netlist, which is an encoding of the logic that is the IC realizes. So this looks like the picture of the full adder circuit from the previous slide. A netlist is synthesized into a layout, which is then manufactured. So we have a die, and finally we have the packaging into an IC. Reverse engineering, which is the attack, does the sort of the opposite of this. So an attacker depackages the IC and then delayers and then uses some image processing and then finally extracts the netlist. So what I'm going to do is talk to you about two techniques that have been proposed, and one of them has been commercialized, and the other one has been partly commercialized. So this is not just research that is on paper, even though the research is quite technical, and I'll mention the aspects of computer science and engineering that is part of this research. Now, one of the techniques I will present, it turns out does not work. So it's kind of like a negative example. And the other one, it appears to work. So let's go through those. So here's a possible solution to this IP theft problem. And the picture to the left, the black and white picture, is taken straight out of a US patent. There's a patent number. You can look it up if you want. And the idea is the following. The problem is when an attacker reverse engineers the IC is that they're able to recover the netlist and see the gates and the wires. What if at least some of the gates appear to be the same? And this is the sort of the idea of a generic gate, where let's say you have 10 gates in your circuit and 5 of them appear to be this generic gate where from carrying out the reverse engineering delayering attack, the attacker is unable to tell what those gate types are. That would, of course, seem to hide the description of the logic in the circuit. So this is the idea. The idea has been patented, like I said. Now the colorful picture to the bottom right, it kind of shows you a cross-section view of this generic gate, and those numbered boxes 1 through 19. They're actually connection points, and depending on how you choose them, you get a different functionality for the gate. So for example, an AND gate might correspond to points 14, 6, and 2 being actually fused, and all the others being not fused. And the whole idea is that this is happening at such a microscopic level that an attacker is unable to tell which ones of those connections are fused. So the whole point is, even though one of these gates appears as a sort of a generic gate, as I'm calling it, when you actually exercise the digital IC, it functions as the gate that you intend. For example, an AND gate, an XOR gate, or something like that. So that's kind of the idea. So to step back a little bit on defender versus attacker, defender has a circuit that they start with. So for example, that simple circuit to the left, which has two NAND gates, G1 and G3, and one NOR gate, which is G2. The defender selects some gates to camouflage. Now you might say, well, why not camouflage all the gates? And by camouflage, I mean replace those gates with what I call the generic gate, which will function correctly as intended, but will appear to be the same. So one of the questions is, well, why did I choose just two of those gates to camouflage and not all three? Well, the answer is that there is a cost to adopting a generic gate as opposed to the original, just the simple kind of gate. The generic gate has a bigger footprint in terms of power consumption, in terms of area. So there is a cost. So really what you have here is a very interesting technical problem, and many technical problems have this attribute of a trade-off. So your benefit is security and you want to camouflage as many gates as you can to get as much security as you can. On the other hand, there is a cost. With each additional gate that you camouflage, you incur an additional cost. So really what you want is to camouflage the fewest gates so that you can get the most security that you can possibly get. Okay, so the defender's job is to choose those gates wisely so that their cost is not prohibitive, and yet they maximize the security or get the security level that they want. What about the attacker? So that is the picture to the right. So consider the following situation. The attacker buys two instances of this IC from Radio Shack. Of course, the IC is camouflaged, so they destroy one of those ICs by subjecting it to the chemical and physical process that I showed earlier, which is the delayering and the reverse engineering. So that effectively destroys the IC, but then they are able to recover this netlist, which is shown on the right side, which is two gates are G1 and G2 are those generic gates, so they don't know exactly what those gate types are. G3, they know that it's a NAND gate. And the other IC, what they can do, the other instance of the IC is a working copy of the IC. So they can actually exercise that second IC with inputs, like I showed to the left of the figure to the right. So for example, 0, 0, 0, 0. And then they can see what output is produced by the IC, right? Now, one other piece of information the attacker may have is they may know the different possible kinds of gates that each of G1 and G2 may be. So this in IC parlance is called a technology library. So in this example, the designer of the IC, it turns out, it's public knowledge that this designer, their technology library comprises NAND gates, NOR gates, and XOR gates only. So now you can, we can apply some logic and observe that there are really 9 different combinations of G1 and G2 together, 3 times 3, because there are 3 possibilities for each of G1 and G2. Now the circuit takes 4 inputs. So there are 16 possible inputs, which is 2 to the 4. Now, if you could exercise the working IC with all 16 inputs and check the output, then you have effectively cloned the IC because you have the truth table that the IC realizes, the entire logic, right? But the thing is, really, the attacker doesn't want to do that because in realistic ICs that have hundreds of inputs, that's prohibitively expensive. You can imagine exercising an IC taking some non-zero time, let's say 1 unit of time. So, if you have to exercise the NIC with 1 billion inputs, well, that's 1 billion units of time, which might be prohibitive for the attacker. But in this case, what the attacker would hope is, well, if the attacker can smartly pick the inputs, maybe by observing the outputs, they can eliminate some of these 9 possibilities. So from the defender's standpoint, what they want to do is make this process, which is eliminating from the different possibilities that these anonymous gates could be, hard. So in this case, ideally, the attacker would have to exercise 9 different inputs to finally arrive at the correct gate types. Okay, so now I'm going to go to the bad news where, even though this technique seems to have promise and it's been patented and commercialized, it does not work. Why does it not work? Well, it's kind of like what I just said, which is that To take this example, so there are the 9 different possibilities of G1 and G2, given the technology library that we adopted. And it turns out that if you exercise the working copy of the chip with the IC, with input 0, 0, 0, 0, and you observe the output, well, you observe that the correct output is 0, but 5 of the combinations yield the incorrect output of 1. So you can immediately eliminate those 5 possibilities from consideration. So this is kind of a problem for the defender. The fact that just by exercising the working copy of the IC with 1 input, the attacker is able to eliminate 5 out of the 9 possibilities. And in this example, it turns out that all you have to do as an attacker is, if you happen to choose those inputs wisely, and those, they're shown at the top, right? If you happen to choose, exercise the working copy of the chip with those 3, you will have converged to the correct identities of G1 and G2. So this is the problem. Now, I'll give you a 20,000 foot level view of the attack. So the idea is this notion that the label of the gears to the top right shows, which is that of a discriminating input pattern. What is a discriminating input pattern? It is something that helps you distinguish between 2 possible guesses for what the anonymous gate types are in a manner that both of those guesses cannot possibly be correct. So for example, you saw in the previous slide that 0, 0, 0, 0, that input for that circuit, it eliminates 5 of them, right? So that is a discriminating input. So the set of all inputs is certainly discriminating, because if you can exercise the working IC with every input, you have enough time and resources to do that, then you will have reproduced the IC. Great. But what the attacker hopes and wants is to identify the green oval, which is a small set of discriminating inputs that will fully characterize the circuit, because then they will have de-anonymized those gates. Now, how do you go about doing this? Well, there's some computer engineering and computer science in there. For example, computational complexity, which is you can think of it as subfield of algorithms. And I can certainly point you to our paper to, so you can see how it works. And we built a tool chain out of it. And well, so here's a little graph showing the effectiveness of the attack. So the hope was, so on the x-axis, on the horizontal axis, what we have is benchmark circuits. They have these kind of names, C5315, C7552, and so on. And a particular technique that's been proposed before in the past is something called the largest clique technique, to choose the gates that will be replaced with these generic kind of gates that will be anonymized. The hope is, that it takes the attacker, for example, in C5315, more than 10 to the 13 years, which is a long time, before the attacker can de-anonymize the circuit, decamouflage the circuit. But it turns out that if you adopt our technique, which involves some, some technical depth, identification of computational complexity of the attack, for example, it turns out that you can de-anonymize, decamouflage the circuit in seconds. As you can see, less than 500 seconds or 200 seconds. In fact, of the 5 benchmarks shown here, you can see that the most time that we take is about 2,500 seconds, which is about 45 minutes, which is really not very secure, right? Especially when compared to what you would hope would be the bar on the attacker. So let me present you some positive, constructive news. I'll confess to you that I'm not a big fan of working on attack techniques at all. It's just that on that occasion, we felt that we really had to point this out, that it was not effective. So let's go to a more constructive endeavor, which is to identify or think of an effective defense technique. So let's go back to the adder circuit. So here's an idea. Why not use the homogeneity that's in the circuit as it is to obfuscate it? So specifically, suppose we remove some of the wires in the full adder circuit. You observe that gate 1 and gate 3 are both XOR gates. Gate 2 and gate 4 are both AND gates. So a possibility is to make gate 2 and 4 indistinguishable from one another. Well, how can you do that? Because if you look at the full adder circuit, they are distinguishable, right? Gate 2 takes as input A and B. Gate 4 takes as input, the output of the AND gate and Cn. So they are distinguishable, of course, in the original circuit. But if I remove some of the wires, so you see the obfuscated circuit down at the bottom, right? And if you assume that the location of those gates in the obfuscated circuit does not reveal any information, then 2 could be either one of V or W. So this is really exploiting the heterogeneity, the homogeneity of the circuit. So we're sort of dead in the water for the gate 5 because it is the only gate in the circuit of type, which is an OR gate, and it is uniquely identifiable. So there's nothing you can do about that in this example. So what you really hope is, well, if your technology library is of size 3, as in this example, you're using only OR gates, AND gates, and XOR gates, then in a realistic IC, which has at least hundreds of gates, there'll be a minimum of a certain number of gates of a certain type, of any given type. That's what we're really hoping for. Now, it turns out that this notion of security is quantitative, and it's exactly based on how many gates look identical. So in this case, for example, you can see that the gate 2, and by the way, these labels, 1 through 5, the picture to the top left, and the labels, X, V, U, and things like that, I mean, they're not actually on the net list, right? I mean, these are just, I'm using them in these slides to identify the gates. And that's why I take the liberty of changing the labels from numbers to letters. So the thing is, gate 2 could be equally likely to be V or W. That's the intent. And this notion of security is quantitative because here, for example, you could say that gate 2 is too secure, which is that there's a 50-50 chance. In realistic circuits, for example, you could go up to 50 security, for example, meaning given any gate, it is indistinguishable from 49 other gates. So that's one aspect. Now there is a cost, which is the number of wires that we are removing. And then of course there's a natural question, which is that, well, I mean, if you remove wires, the circuit doesn't work as intended. I mean, it just, the circuit, the obfuscated circuit is not an adder circuit anymore. Well, we're already aware of a certain technology called 3D IC technology, which was being used for other reasons, scalability, in fact. And this nice picture to the left is a Xilinx FPGA chip, which leverages 3D IC technology. So 3D IC technology, as the name suggests, if you think of an IC, you think of a two-dimensional thing, meaning a plane, but you can stack these one on top of each other, and that way you can scale. Well, we are using it for security. So the picture on the right shows a kind of a cross-section of the way we would do things. So what we would do is, so we have 2 layers, let's say. We have the blue layer at the bottom and the red layer at the top. Now, what we're doing is we're only removing or lifting, as the word is, lifting wires from the blue layer, and we're going to reintroduce those wires so that we eventually have a working IC, an IC that works correctly, in the red layer. Now, there are a number of interesting things here. The first thing is that if you look at the blue layer, that is the only one which has gates, and so that is the only one that needs silicon. The red layer, some folks would call it a metal-only layer because the only thing it has is wires. So this is the manner in which we can reintroduce the wires. Now, this by itself is not enough. We also have to kind of consider the IC design and manufacturing process. And we have to be very careful in how that is organized to get security. And really here, security comes from what we can think of as separation of duty, which is doing the 2 things in 2 different places in a manner that you hope that those 2 do not collude with one another. So I'll call attention to towards the bottom of this picture, where you see that after the routing step, we send the lifted circuit, which is the top circuit, which is the metal-only plane, for fabrication to an in-house fab, for example. And the unlifted circuit, which is the one which has silicon, we outsource it. And the reason we may do this is that the metal-only plane is much cheaper to fabricate, right? So what we're suggesting here is lift these wires and then, fabricate a piece of the circuit in a cheap way in-house. And the unlifted circuit you can send to the, fab facility in some untrusted part of the world, and they can do the mass production, and they wouldn't be able to de-anonymize your circuit. They wouldn't be able to steal your IP. And then, of course, you have to put the two layers together, and that can be done. We're suggesting that that doesn't require a trusted house. So the green parts are done in a trusted facility, and the parts that are not green, you can do in an untrusted facility. That's the idea. Okay, so that's it for my little talk on digital ICs and security. That gives you a little bit of a sample of my work. And there's a lot of work happening at Waterloo Engineering, and certainly myself, that relates to IoT. So for example, we have this big project right now, and I collaborate with one of my colleagues, Catherine Rosenberg, on communications, 5G, which is the next cellular standard. I continue to work in digital IC security. We have some work going on in cloud security. For example, we have found some issues with Amazon Web Services, which is, of course, the 10,000-pound gorilla in cloud computing. Lots of research opportunities for undergraduates. If you're an undergraduate right now at Waterloo or plan to join, you can certainly talk to any of us. And there's always grad school. So that's it.
All right, thank you so much, Professor Mahesh Tripunitara. And from that, we can really understand that in the field of IoT and such as digital ICs, that something like security is a very important issue with so many interconnected devices and transferring of so much data. Security really becomes something important and something that we need to address. And on to our next panelist, we have Professor Srishanta Mitra. Professor Mitra received his PhD in mechanical engineering from the University of Waterloo. He is the current executive director of the Waterloo Institute for Nanotechnology and a full professor in the Department of Mechanical and Mechatronics Engineering. He is also the founder of the Micro Nanoscale Transport Lab in the University of Waterloo, where they conduct fundamental studies related to fluid transfer processes. And today he's here to share with us his knowledge in the field of IoT.
Okay, I'd like to share the screen, I guess. Are you able to see my presentation?
Yep.
Okay, thank you so much. Professor Mahesh has given a fantastic introduction about the intricacies of IoTs and so forth. So in my talk, what I will focus on is essentially some of the applications where we see IoT and mobile platform can be used in some of the application areas. So this is the nice background of my institute, the Waterloo Institute for Nanotechnology. It has this graphene structure that you can see at the background. So if you look at the WIN, the acronym is the Waterloo Institute for Nanotechnology. The acronym is WIN. It's really looking into this Industry 4.0 agenda, and way we see ourselves in the research enterprise is we start all the way from the quantum phenomena, looking at the angstrom scale, and then through that understanding, we build, be it two-dimensional materials, or even nano machines that can be, used as ways to manipulate objects at the nano scale. And so all the way from understanding of the angstrom level physics, we move into nanometer scales where we have some tangible objects that we can manipulate. And then we move into this micro scale, which is makes more in terms of the real devices, so to speak. These are sensors, actuators, and so forth, which are in the like micro electromechanical systems. Those are in the micron scale. So a micron is typically, if you think of your hair, it is 100 microns. So that gives you an idea about what the length scale we are talking about, these small, teeny tiny device. Now these devices then react with the real world, because you have to have our real world is unfortunately is a macro scale system, because where the sizes are typically in millimeter, meters, and so forth. So they get embedded into these various device, systems. Say, for example, a watch which is able to measure how many steps you are doing every day. So it has a small gyroscope, is a MEMS-based device, is a microsensor. Then it gets articulated into a macro scale system, a real world system. And through that process, what we are doing is we are bringing IoT, we are bringing big data, machine learning, all these intersections and convergence of these things happening at this arena where sensor world meets with the real world application. So at the Institute, we are able to bridge across the entire length scale, if you will, from all the way from angstrom to a meter scale. By doing so, we are able to solve some of the global challenges, be it in energy, be it water, be it public health. For example, in today's scenario, COVID-19 pandemic, public health is becoming more and more important than ever before. So all these things we are able to provide a meaningful impact, not only the economic impact, but also societal impact in a bigger way in the Institute. So I will, in the next few slides, I will focus on how we see one of those global challenges, water, and how we see some of these mobile technologies and platforms could be integrated in our effort to make it technology for the masses. So water is a global challenge because there is a huge scarcity of water resource, particularly in terms of the drinking water is a real challenge. You see, access to safe, clean water, particularly to the populations where there is water scarcities in developing worlds, in sub-Saharan regions of the world, this is really a challenge. In Canada, we are quite fortunate. We have some of the largest freshwater lakes here, and so we have an abundance of potable drinking water, but not always the case. So when we see in water, one of the bigger challenges is the E. coli. And that is also in North America. For example, in the middle picture shows in the United States, there's a lot of well water. So particularly the remote communities, we see the well waters, and then there is E. coli outbreaks. So E. coli is a pathogen, which is a waterborne pathogen, which even all animals and human beings also have in our gut, E. coli. However, the challenge is when due to rainy season or due to some runoff or due to cross-contamination between sewage line versus where water distribution is taking place, so E. coli can appear in our potable water, and that could be dangerous. And this is exactly what happened in Walkerton. This is 2004. Maybe some of you was born at that time, but this was a big embarrassment for our province because having, as I mentioned, we have such a huge amount of potable water, safe drinking water, but still we found that in Canada, particularly in Ontario, we had this E. coli outbreak. And the people was drinking this contaminated water. The challenge was there was not enough quick sensor that could monitor the E. coli right at the source of the drinking source water, so that before it goes to the distribution network, people can actually know, wow, there is a E. coli outbreak, then I shouldn't drink water. And the easiest way is to create a water boiling advisory. So the municipality, the health agencies, immediately public health agencies put forward a boiling water advisory. And unfortunately, this never happened. And then people had a huge challenge with E. coli outbreak. So how we do this is we come up with an engineering solution. I will not go into details of it. It has a lot of chemistry in it. but essentially we target one of the enzymes in the E. coli, and we are able to do a very quick test. This is, for example, like any good chemist will do. We mix a lot of chemicals, so it looks like a cocktail of chemicals. And then if you have a no E. coli versus if there are 4, this is CFU, coliform unit per ml of E. coli, so the color changes in the centrifuge tube, so it indicates there is an E. coli present in the water. So this is a good experiment in the lab scale, but the question is how we would able to make this in a device that will be field deployable. So we came up with this mobile water kit where we take water sample, then we pass it through through these millipore filter. So these filters have a pore scale which is 0.45 micron. So if you think of E. coli, the E. coli length scale is 100 typically a micron or so, a few microns and so forth. So if there is an E. coli in the water, so they get stuck into these filter surfaces, the white surfaces of the filter, and then we use this chemical compounds A, B, C, D in a sequential fashion, and then we see there is a color change happening on the pristine surface of the filter surface, which indicate there's an E. coli. So we realized, wow, this is great. So we are able to create a device which we can deploy in the field. But also we realized when we did field trial, a lot of these places where they don't have access to clean, safe drinking water, but they have access to cellular network. Because nowadays the connectivity is so critical, and people have that advantage in some of the limited resource communities of the world. And we said, let's take advantage of this cellular network. So what we did is we came up with an Android-based app where it's where the people or typically the NGOs who go to different well, test the water, take the picture. So this is a picture from a cell phone image, then it's sent to a server. It tried to do a match. If, for example, if there was no E. coli, the filter surface is completely white. If there is a color change on the filter, then we have taken that cell phone and cellular number of those well users, and it sent a small, text message to the well user saying that, hey, you can't use this well because it's contaminated. So through this distributed network system of these sensors, we were able to capture a huge amount of data in terms of the water quality. We further improvised based on the field trial. We came up with a much nicer ways, a single device. And again, you use the smartphone, and it goes into a cloud server, which then does the data analytics, and then will let us know if there is a E. coli present or the water people can drink or not. We also created a very frugal device, I will say a frugal innovation, which is this stick that you see is a DipTest. It's like a litmus paper. It's made up of paper, what we call it paper microfluidics. And if there is an E. coli present, the color change happen on the strip. So it is similar to the concept of a pregnancy test strip. It's a similar kind of a test strip. It is frugal. It's a few cents. You can carry, for example, if you are doing a camping, you can take it with yourself, take a water, put it in your glass and see if the water is safe or you need to boil the water and so forth. So we see that this is a very powerful tool. So what we do is we created we made it predictive. So we have a huge amount of data set, what we call is a training set of E. coli images, and we put a convolution neural network where we train the network in all these images of different concentration of E. coli, because these are not only the spike sample tests that we do in the lab, but also in the field data that we get. And then based on the images of on the sensor that we get, we can train the data so that, for example, if there is an unknown concentration of E. coli present, if we do a testing and we find, hey, there is a color change, now we can precisely tell whether what is the concentration of the E. coli, because for example, recreational water as per the US EPA, Environmental Protection Agency, is required that you can have a recreational water, that means which we can bathe, we can take swimming in pools, maybe 120 CFU per 100 ml. Or whereas drinking water, it has to be 0 CFU per 100 ml. However, this color quantification method will not give you a precise, say for example, whether it's 10 or 12 CFU per 100 ml, but it gives you a bin. For example, whether it is 150 or 200, 250. So that range is important, because if anywhere beyond certain, for example, if it's in the swimming pool beyond 150, you will not go into the pool unless there is a effective treatment. Typically in the swimming pool, you do chlorination and so forth. So what we see is that IoT and these your cellular platform creates an integrated water management, because we take data, or we put the sensors in wells, in different hand pumps, in remote locations, in water taps. Then we do these things. We similarly send the blind sample to the labs, where these are pathological, water quality test labs, where we grow the bacteria, do a cell count, and then also we validate our sensor data. Then we send those sensor data right into a server, which do the data analytics with the IoT platform, and then it can send the messages out into the cellular network. That's in power, even though they don't have access to clean water, but everyone has a cell phone. So in the morning, they check whether the well they want to access water is clean or not. If it is not clean, then they go for another well and so forth. And also it alerts the public health agencies. For example, the doctors, local doctor can do chlorination. That's the cheapest way. They can dump chlorine. Of course, this is the challenge. If you have residual chlorine in your body, that also is not good. So you have to have a continuous monitoring system. So this is kind of an integrated management, water management with the application of IoT and cellular network. We find it very important. And of course, some of the security issues that Professor Mahesh has talked about, these are integral to the resilience, to create a more resilience network for these kind of system. So thank you for your attention. This is my email. Feel free to email me. You can go to my institute website, as well as my research lab website as well. I'm happy to take any questions, comments as well. Thank you.
All right, thank you so much to Professor Mitra for sharing the details with us. And we can see that there are some very extensive applications of IoT. And when it comes to, especially in the medical field, the importance of transferring data to important medical personnel and making sure this data is secured and transferred correctly. And with that, we'll move on to our Q&A session for today. And without further ado, we'll start with our first question. And either one of you guys can answer this question, feel free. So the first question is, where should a beginner start in the world of IoT?
Jackson, can you pick one of us?
If you guys would both like to answer, sure, we can start off with Professor Tripunitara.
Well, I mean, I don't know, going to university is a good start, because I mean, this is a technical field. And I don't know, one has to start kind of at the beginning is what I would say. And there's a lot of aspects to IoT, right? I mean, just from these two presentations here, it should be apparent. And so depending on whatever aspect it is, I mean, what Professor Mitra is working on is fairly technically sophisticated. What I'm working on is fairly technically sophisticated. And these are not pie in the sky kind of things. These are realistic, real world things, right? And they do require some good technical training in various aspects of science, engineering, math. So yeah, that I would say that is the first step.
And if I may add, since there are some young minds here, maybe, work with, and if you're a high school student, maybe come to university, spend some time in Professor Tripunitara's lab, and maybe go for a science fair. You know, we have Waterloo, Wellington Regional Science Fair, where you can maybe help to create some of your inside curiosity in terms of where your passion in terms of applying IoT, and maybe showcase some of the demo. Maybe that's a good way to kickstart some of our tangible, connecting with our university research ecosystem, as well as connecting with the community, where there are young minds who are also in the science fair. You can learn from each other as well, from your peers.
Yeah, I definitely agree. The university and just this area in general, there's a lot of opportunities where there's so many young minds working together to progress in the area of IoT that you can definitely find something that you would like in that area. And on to the next question. So it is, what about IoT is the most exciting for you looking into the future?
You were muted, so I think we lost your last part.
Oh yeah, and yeah, if you'd like to start, that was all.
Who's the you? Is it me?
Yeah. Sorry.
Okay. So for me, there are a couple of interesting things. So the certain expertise I have, my degrees are in math and computer science, even though I'm in engineering right now. So, I mean, I love discrete math. I love algorithms, computational. I mean, so there's certain mathematical logic. So that kind of stuff turns me on. So any problem that involves that kind of thing, I'm very interested in. But the other aspect I would say is about IoT in particular is sheer scale, right? So some people refer to the internet as the largest distributed system that has ever existed. And that's actually true. And the amazing thing about the internet is it kind of sort of works. And there's certain, it's not by accident. There's certain key design choices that have been made as part of the internet, that are part of the internet, that actually have led to it working. So what is an example of a design choice, in my opinion, in my mind, is that the internet is a packet-oriented network, not a stream-oriented network like the phone, the old telephone system is. It's actually more like Canada Post, where you send the discrete packets, right? That was a choice that was made. Another choice that was made is the internet is a best effort packet delivery system. Again, like Canada Post first class mail. It's not a guaranteed delivery system. And it turns out that you can build a guaranteed delivery mechanism on top of this best effort mechanism. Anyway, there's a lot of these, and then the autonomy that each agent has. So if you go to IoT, well, the intent is really for it to function as internet on steroids. So the scale that people are talking about for IoT is 1 or 2 orders of magnitude more than the internet. The heterogeneity of devices is, it's much more than the internet. So this, I think, is a particularly exciting aspect of IoT, in my opinion. The sort of the heterogeneity, the scale, and the systems aspect.
And if I may add, I think the scalability is very critical, as professors mentioned, and also the convergence. We are seeing a lot of the technologies looking IoT and machine learning, others getting that convergence part is quite exciting that way as well.
Awesome. And on to our next question. The question asks, what are some good beginner IoT projects that's related to current real-world applications? And what are some career prospects for IoT specialists and development of future areas in the of the application of IoT? And at this time, we'll switch it up and have Professor Mitra start.
So I just gave an example in the water area, right, in where sensors can work. And I think this is similarly in a distributed network of, any kind of, if you think of a network of, vehicles, for example, that also there is a significant usage of this. Excuse me. Even people are talking about large-scale engineering systems like power plants, where IoT will be, used in a very big way to look at how these kind of different power plants can be integrated and so forth, and mixing of energy resources. For example, if you have in certain peak hours, you may need certain renewable resources to come in. So I think those things, quite an energy mix, can also be utilized through IoT platforms. So there is a huge opportunities. Thank you.
Yeah, so I would actually echo Professor Mitra's comment about the scalability again, right? So to me, the first thing I will say is, as a matter of philosophy, is I think any problem of scale is an interesting problem and a potential application area for IoT. So let's take some examples, right? And I think in terms of the example I'm trying to give you some examples from the standpoint of the question, which is, well, what are some areas that one can get into? And I think it's pretty much any area that you are interested in. So a couple of examples that came into my mind are, the other day I was reading about the number of new species that are discovered every year. It's a surprisingly large number, right? So there's, I don't know, hundreds or thousands of different species that are being discovered. We didn't even know that they existed, right? So this is a problem of scale, of some heterogeneity. I don't know where they're being discovered, right? So is this something that can be eased with automation, some of the devices and technologies that we're talking about here? That's an example, right? Another example is recently me and some of my colleagues in the Faculty of Health here at Waterloo, we have this rather large grant application, and the problem statement really came from our colleagues in health. And what they're talking about is, well, if you look at Canada and you look at the older population, Alzheimer's is a big killer. And, lots of people are susceptible to Alzheimer's. The amount of money that is being projected to be spent and is already being spent on health, taking care of Alzheimer's patients, right? And Alzheimer's has a certain evolution. And I learned all this from working with our folks in health, which is that, the last stage of Alzheimer's is really dementia. So there's a question as to, well, you technologists, can you help with this in some way, right? So where I'm going with this is, I feel that pretty much any area that we look at, biology, health, I don't know, journalism, I can think of problems, right? I think that one will find something that is interesting and one could potentially put in a context of IoT. And that's really the intent of IoT, right? It's to the hope from technologists is that it permeates our lives more than it already has. I mean, in some ways it already has, but even more in good ways.
Yeah, and I absolutely agree. Especially with all this technology coming in, most of them are coming in together to kind of like use our lives and integrate like kind of the existing technologies together to kind of form something that we can kind of build off of. And on to our next question. It's a bit of a long one. So question asks, you mentioned the homogeneity of IoT devices. Interconnecting a large number of devices comes with a handful of new entry points for cybersecurity risks, such as increased vulnerability for creating botnets for DDoS attacks, and the creation of new vulnerable entry points to other sensitive connected devices. I was curious if you could educate us on what measures the IoT industry is coming up with to regulate and mitigate these risks on top of protecting the IP of circuits themselves. How do you think the development of these devices should be regulated? And with the growing rate of the industry, how effective do you think regulating IoT devices will be in practice? So I think if Mishesh could start off with me.
Yeah. So, I mean, there's lots of challenging technical problems in this space, and security is certainly one of them. I can tell you that the Defense Advanced Research Projects Agency, DARPA, in the US, which is actually credited with a number of innovations, for example, related to the internet even. They are recently funding a research endeavor in the security of digital ICs, but I don't think we have a good handle on it yet. So I think it's well recognized, especially the IC stuff, well recognized as an kind of an Achilles heel. I'm trying not to get too controversial, but it's kind of an open problem is what I would say. So that's part of the reason people like me are still interested in actively working on it. And it's a very challenging problem. I feel that to effectively work in that space, one really needs strong background in discrete math, logic, algorithms, I mean, all sorts of things, right? It pulls that together. Now, in terms of new devices, well, I mean, it's kind of all over the place. So for the longest time, Microsoft was being beat up by folks because the perception was the homogeneity of Windows, because so many devices were running Windows. That homogeneity was a problem, because if there's a vulnerability in one machine, it exists in a billion machines, right? So some people would argue that heterogeneity is a good thing. But the problem with heterogeneity is, well, is this all brand new code that's running? If so, what kind of vetting has been done, right? So again, I would say that we don't really have a clear answer on any of this. So your question is a very good one. And unfortunately, I cannot give you a slam dunk answer.
And if Professor Mitchell, yeah.
May I ask, maybe it is a good opportunity for me to ask Professor Mahesh, because I'm very curious about the security part of it. I'm just wondering, is anyway, for example, blockchain and encryption technologies is of any use in this kind of creating more resilient IoT network?
Well, it can be. I think we just have to be cautious, because to me, so for example, let's take encryption, cryptography more broadly. Okay, it's a toolkit. Is it actually effective is one question. And the other question is, I mean, when we look at the systems problem, so for example, your water management system, let's say I bring in some cryptographic aspect, right? Well, it's a bit like, to use an analogy, okay, I might have a really strong lock on my front door. That is my cryptographic technique. But I end up hiding the key under the mat, under my front door, right? And that undermines my security, right? So when we look at a system, well, it's not enough to look at the mathematics of crypto and how strong it is, and that's all wonderful, right? But how you actually put the system together, that is really challenging, right? Like, how do you manage keys, for example? Who your users are? I mean, are you making it easy for them to do things? So even at, just as a quick example, at Carnegie Mellon, one of the people I know from my research community, he convinced many of his colleagues in the same hallway and the same building to replace their their doors with fingerprint, right? And it was a very interesting study, because it appears that if I can do fingerprint access to my door, it makes it much more usable and convenient. And I don't have to carry a key around. But what they did not anticipate is some of the practical problems with introducing fingerprint technology. So for example, you have a reliability problem where somebody, for some reason, maybe their DNA or what their finger is like or their age or something, always had problems unlocking the door. So they ended up exhausting all their fingers. I mean, you only have 10 fingers, right? So they trained the thing with their thumb. Okay, then it started malfunctioning. So then they trained it with this, and then they ran out of fingers. So just as an example of a problem, right? So I think that, to me, security I mean, I talked about in some ways the easier security problem of focusing on an IC. But if we look at the system, for example, your water management system, I mean, that's a whole nother ballgame. So whether blockchain is useful, I would have to look at the setting. So we associate some properties with the blockchain, which is that it's a ledger, which has integrity and cannot be modified after the fact and so on. And you have to commit. There's a notion of a commitment that you make. Well, is it appropriate for my application? I don't know. I think we have to really look at it closely. So I can tell you that one of the largest telecommunication vendors on the planet that we collaborate with, I won't name them, recently told us that, well, in our company, blockchain is now a bad word. We feel that it has been oversold. Please don't even mention it to us unless you have a compelling case for it.
All right. And so I think this is our final question for the day. How common is it to see people getting hired for software engineering jobs without an SE degree? Will software engineering ever crash into a bust cycle after its boom? And if so, what will be the cause? So for example, like too many SE graduates with not enough jobs to fill the market.
Should I answer this, Sushanta? unless you're familiar with maybe you're more familiar with this. I did serve as the Associate Director of Software Engineering for 2 years. So I had to learn. Is he still there? I can't hear him.
Yeah, please go ahead. I think
okay.
you are the best person to talk about it.
Sure. So maybe Jackson can answer this too, right? Based on your experience in the program. The short answer is yes, absolutely. I mean, lots of our CE grads, Jackson, you're in computer engineering, right? Yeah. Mechatronics grads. I mean, lots of them go into software engineering jobs because those are the ones that are most prevalent. In my view, certainly in Waterloo, by the time a CE graduate graduates, they can pretty much make themselves indistinguishable from an SC grad, depending on what choices they make, for example, with the technical electives and things like that. So in my opinion, it doesn't really matter all that much whether you go into mechatronics, software, even EE, right? I mean, you could kind of bias yourself towards the end. Now, with regards to will we exhaust software engineering jobs? Well, presumably there's some kind of threshold, but I don't think we are even close to it. And the reason is, what is perceived as software, I mean, the tentacles have extended so deeply in so many industries. And people have tried all kinds of things, right? Like, so for example, if you assume that you're RBC, Royal Bank of Canada or Bank of Montreal, you're not a software house. You don't want to build software. You don't want to have to maintain software. So ideally, you wouldn't even hire a single software engineer. They cannot get away with that. Same thing if you're Loblaws. So for example, it turns out that Loblaws Digital apparently hires co-op students from Waterloo. And I've heard from some of the students that it is a great co-op job. Apparently, it's a very enjoyable co-op job. So just as an example, right? Like I think of Loblaws as a grocery store. I don't think of them as hiring computer engineers and software engineers. But the thing is, these technologies have become so pervasive that there's no choice but for even a grocery store chain to hire these kind of engineers, right? So I think that there's probably some kind of threshold, but I don't think we're even close to, exhausting that. And sure, you're going to go through boom and bust cycles in Silicon Valley, for example. So one might get unlucky and graduate, for example, from the Waterloo SCE or CE program when it's a bust cycle. I think somebody like Jackson is well positioned because he's in second year right now. And I expect that in about 2 to 3 years, they expect that the US economy will really recover from COVID-19. And then he's going to be really looking at a whole bunch of, it's going to be a feeding frenzy for him.
Let's pray for that, yeah. And to Professor Mitra, do you have anything you'd like to add to that?
No, I don't have anything. I think he covered pretty much everything.
Yeah, and I think well, obviously I have less experience in the area, but I think I would agree with Professor Tripunitara on that, and that there really is a lot of different areas in software developing. We can go into so many different areas, and there's countless co-ops on Waterloo co-op jobs. If you just like during our co-op terms, there's so many that you can like apply for, and really like the opportunities are endless. And I think that is definitely something that it shouldn't be really a top concern when considering an SC degree. And with that is our last question for today. So thank you all so much for your intriguing questions. And we hope that we were able to provide you with some more insight into the field of IoT. And of course, this would not have been possible without our two wonderful panelists, Professor Sushanta Mitra and Professor Mahesh Tripunitara. So I'd like to thank you two so much for your time, and I'm sure the audience is very grateful for your time as well.
It's such a pleasure. Really enjoyed.
Thank you. And as well, I would like to thank every PTC Waterloo exec behind the scene for making this happen, as well as all the execs from all the regions and branches of PTC who supported planning this panel and sharing it in their network. And if you'd like to learn more about IoT, University of Waterloo, we will send out an email shortly after with additional resources. And if you have any questions you'd like to ask us, email us at waterloo@projecttechconferences.com. And I'm sure, I think I saw both professors send out their contacts. If you have any questions for them, I'm sure they'd be happy to answer. And as well, do be on the lookout for upcoming events by PTC. So be sure to follow our social media. and tune in for many events to come. And with that, that concludes our panel for today. And I hope everyone has a wonderful evening and stay safe.